Greetings students. This is second online lecture of nuclear physics. In this class, we are going to discuss about Q value equation, threshold energy of an endoergic reaction. After this lecture, you will be able to understand about what is Q value, how Q value equation can be found, energy balance in nuclear reactions, what is threshold energy, and expression for threshold energy. In addition, we will also discuss a few problems relevant to Q value and threshold energy calculations. The Q value equation for a nuclear reaction, or otherwise nuclear reaction kinematics. In the study of nuclear reactions, an important parameter of all the nuclear reaction experiments is the measurement of the energy released in the reaction, which appears as kinetic energy of the residual nucleus and of emitted particles, or as the energy of the photons that set free at the expense of the internal energy of the colliding systems. This energy is called the Q value of the nuclear reaction. This Q value is related to energy involved in the nuclear reactions, in which an amount of energy may be absorbed or released during the nuclear reactions. So we shall derive the Q value equation for the nuclear reactions in the next few slides. This picture explains collision of a projectile with a nucleus and the energy involved before and after collision. Here m1 is the mass of a projectile, v1 is the velocity of the projectile, ek1 is the kinetic energy of the projectile. m0 is the target nucleus rest mass. m2 is the recoiling nucleus after collision. m3 is the emerging particle after collision. Suppose a particle of mass m1 moving with the velocity v1 collides with a target nucleus of mass m0 at rest, as shown in the picture. After collision, the particle O of mass m3 is emitted with a velocity v3 at an angle theta, and the recoiling nucleus P of mass m2 is emitted with a velocity v2 at an angle phi. Here recoiling nucleus that undergoes a change in momentum as a result of collision. In this animation, we can visualize the collision of projectile with the target and movement of recoiling nucleus and the emerging particle. You can see the projectile movement before collision, which is with high velocity. But after collision, the velocity of the emerging particle is decreased, since a part of the kinetic energy is absorbed by the target nucleus and became recoiling nucleus with change in linear momentum. When the fast projectile collide with the target nucleus, a part of kinetic energy or even all of its energy can be transferred to the target nucleus. The amount of energy transferred varies with the scattering angle of recoiling nucleus and the projectile. The interaction of the projectile with the target nucleus depends upon the energy of the incident projectile, as we already discussed in our first lecture. In this case, a part of energy is absorbed by the target nucleus and scattered in an angle phi, and the projectile at an angle theta. With these considerations, let's apply conservation of linear momentum in the plane of the screen, which gives the equations as follows. The conservation of linear momentum yields this equation. So in this equation 1, linear momentum before collision is equal to linear momentum after collision. So let's sort out horizontal and vertical component of the particle velocity before and after collision. So it will be m1 v1 cos theta, which is equal to m3 v3 cos theta plus m2 v2 cos phi. Here cos theta, which is equal to cos 0 we know it's 1. Since v1 is along x-axis, the horizontal component is 0. That means theta equal to 0. So the equation becomes m1 v1, which is equal to m3 v3 cos theta plus m2 v2 cos phi. Similarly, the vertical component m1 v1 sin theta, which is equal to m3 v3 sin theta minus m2 v2 sin phi. So here theta equal to 0, since v1 is along x-axis, so sin 0 equal to 0 because there is no vertical component before collision. And negative sign indicates the product and eminent particles are in opposite direction. So sine of minus theta, which is equal to minus sine theta, and cos of minus theta is cos theta. So the equation becomes m3 v3 sin theta minus m2 v2 sin phi, which is equal to 0. From equation 1, m2 v2 cos phi, which is equal to m1 v1 minus m3 v3 cos theta, and equation 2 becomes m2 v2 sin phi, which is equal to m3 v3 sin theta. Squaring and adding, we will get m squared, m2 squared, v2 squared, cos squared phi plus sin squared phi. So we have taken out the common term, which is equal to, so we are expanding with a minus b the whole squared. So the equation becomes like this, and m2 squared v2 squared into cos squared phi plus sin squared phi, which is equal to m1 squared v1 squared plus m3 squared v3 squared into cos squared theta plus sin squared theta. So we have taken out the common terms, minus 2m1 m3 v1 v3 cos theta. And following this, we get m2 squared v2 squared cos squared theta plus sin squared theta, which is equal to 1. So the equation becomes like this, m1 squared v1 squared plus m3 squared v3 squared minus 2m1 m3 v1 v3 cos theta. This is equation 5. So now, using kinetic energy relations, we get ek1, which is equal to half m1 v1 squared, ek2 is half m2 v2 squared, and ek3 is half m3 v3 squared. Here ek1 is the kinetic energy of the projectile, ek2 is kinetic energy of the recoiling nucleus, ek3 is kinetic energy of the eminent particle. So substituting these values in equation 5, we get 2m2 ek2, which is equal to 2m1 ek1. Since mv squared equal to 2ek, it becomes 2m1 ek1 plus 2m3 ek3 minus this term. And since m1 v1, actually the last term is minus 2m1 m3 v1 v3 cos theta. So here we get m1 v1 and m3 v3. So here m1 v1 is root of m1 squared v1 squared, that becomes root of 2m1 ek1. So we are substituting this in order to get the equation. And finally, let's bring the term ek2 on the left hand side. So ek2, which is equal to m1 ek1, the whole equation divided by 2m2. So that's the equation 6. We know that the Q value is the difference between the energy of the projectile and the sum of energy of the recoil nucleus and emerging particles. So the energy released or absorbed, which is Q equal to ek2 plus ek3 minus ek1. So here ek2 and ek3, the sum of this is the sum of the energies of the projectile eminent particle and the recoiling nucleus, the energies involved in this. And ek1, we know that the energy of the projectile. So substituting the value of ek2 in equation 7 from equation 6, we get Q is equal to ek2 value we are substituting here plus ek3 minus ek1. And now Q is equal to, let's take out the common terms EK3. So EK3 is appearing in the second term and one before the last term. So EK3 into 1 plus M3 by M2 minus EK1 is also common in the first term and last term. So let's take it out. So EK1 into 1 minus M1 by M2 minus 2 by M2 and the remaining terms. So from this equation we can find out the energy involved in the nuclear reaction. So this is the actual energy involved in the nuclear reaction. Suppose if theta is 90 degree. So let us say the projectile is scattering with 90 degree. So in such case cos 90 is 0. So the last term of equation 8 becomes 0. Hence the equation 8 can be reduced as Q is equal to EK3 into 1 plus M3 by M2 minus EK1 into 1 minus M1 by M2. And this is the final equation, and this is the energy involved in the equation. That means the Q value. This is the expression for Q value, and this is for the 90 degree angle of the scattered particle. If the scattered particle angle is 90 degree, then we will get this energy equation. Otherwise, equation 8 is the common equation for energy involved in the nuclear reaction. So this is about the energy involved in the nuclear reaction. So now let us discuss about the energy balance in nuclear reactions and the Q value. In all nuclear reactions, the total sum of mass and energy is conserved. For example, let us consider a nuclear reaction as follows: A plus B, which is equal to P plus O. Here target at rest and its mass is M1. So let us say A is the projectile and B is the nucleus and P is the eminent particle and O is the recoiling nucleus. So let us say the projectile mass is M2 and its kinetic energy is E2, and the product nucleus mass is M3 and kinetic energy is E3, and outgoing particle mass is M4 and kinetic energy is E4. Here, since the target is at rest, so E1 is 0. So now let us calculate the equation representing the conservation of total energy, which is M1 C squared plus E1 should be there, but E1, since the target is at rest, E1 will be 0. So this will become M1 C squared plus M2 C squared plus E2. E2 is the energy of the projectile, which is equal to M3 C squared plus E3. We know that M3 is the product nucleus mass and E3 is the energy of the kinetic energy of the product nucleus, plus M4 C squared plus E4. So here E4 is the energy of the outgoing particle. So now we are ready to calculate the Q value. So Q value, which is equal to the difference between the energies, kinetic energies before and after collision, kinetic energies of the particle before and after collision. So here it will become E3 plus E4 minus E2, which is equal to M1 plus M2 minus M3 minus M4 into C squared. So with this relation we can find out the Q value of the nuclear reaction. So here Q is called energy balance or Q value equation. If Q is positive, suppose if we get positive Q, then the reaction is called as exothermic reaction or exergic reaction. Suppose if Q is negative, then the reaction is endothermic, or this is also called as endoergic reaction. The equation for a nuclear reaction now becomes A plus B, which gives P plus O plus Q. That means here Q represents the energy involved in the nuclear reaction. So this Q may be positive or negative. So this is about the energy balance in the nuclear reactions. Now we can discuss about a few problems. So in the first problem, compute Q value for the reaction. So the reaction given is nitrogen plus alpha particle. So here nitrogen is the target nucleus N714 and alpha particle is the projectile, which gives oxygen 817 plus H11, that means a proton, plus Q, where Q denotes the energy absorbed or evolved during the nuclear reaction. So now let us compute the Q value for this reaction. The solution is the atomic masses of the particles. So we need to find out the atomic masses of these particles. So the particles are nitrogen, this is the target, and alpha particle, this is the projectile, and the product nucleus is oxygen, and eminent particle is proton. So let us find out all the masses, and then we can find out by measuring the mass difference. We can find out the mass difference, and by using the Einstein's mass energy relation we can find out the energy involved in the nuclear reaction. So here the mass of nitrogen, which is 14.003 atomic mass unit, and alpha particle is 4.00 atomic mass unit, and oxygen it is 16.99, and the proton it is 1.00. So substituting these values in the equation, so we will get in the above equation we are substituting these masses, and we can get the Q value, which is the difference between these masses. So this is minus 0.001277 atomic mass unit. So according to mass energy, Einstein's mass energy relation, we know that one atomic mass unit, which is equal to 931.3 million electron volt. So let us multiply this mass difference with this mass energy relation factor. So we will get the Q value, this is minus 1.189 million electron volt. So in this case we have got the Q value which is negative. Okay, so this Q value what we obtained here is in close agreement with the experimental value, that is minus 1.26 million electron volt. And this is also incidentally an evidence for the Einstein's mass energy relation. Okay, so in this case the Q value is negative, that represents this nuclear reaction is a endothermic or endoergic reaction. So now let us discuss one more problem. Determine the product nuclei and Q values in the following reactions. And we have aluminum within bracket D comma alpha and magnesium within bracket alpha comma D. So in these cases, actually this is the representation of nuclear reaction. So in these cases we have aluminum, that is the target nucleus, and we have the projectile is D, deuteron, and we have alpha, the eminent particle, but we don't know the product nucleus, so we have to find out the product nuclei. And in the second case also we have the target nucleus, that is magnesium, and alpha and D is the projectile and the eminent particle. So we need to determine the product nucleus from this given nuclear reaction. So masses of aluminum, magnesium, alpha and D, these are given, and finally comment on your results. So this is the problem. Now let us discuss about the solution. So the first solution, that means aluminum within bracket D comma alpha. So let us take this reaction in order to find out the nuclear reaction. So the nuclear reaction is, we have aluminum 1327 plus the deuteron, it is H12, which gives magnesium, because we know the eminent particle from which we can find out the atomic and mass number, and we can get down the exact product nucleus. So that could be magnesium. It is magnesium 1225 plus alpha particle plus Q, the energy involved. So now let us find out the energy involved in this equation. So Q is the mass difference, obviously, so that gives 0.0073 AMU, and we are converting it into the electron volts by multiplying 931.3 million electron volts. So the AMU is multiplied with this factor and we got 6.797 million electron volt. So this is the energy involved and it is positive. Now let us move on to the next equation. So substituting these values in the equation, we get magnesium 1225 plus alpha, it is the projectile, which gives a deuteron plus Q, and we can find out the atomic and mass number, and by substituting that we have got aluminium. So aluminium is the product nucleus, and from this equation, by substituting the mass values, we can find out the mass difference. So that gives the Q value, and here the Q value is minus 6.797 million electron volt. So the Q value obtained is negative. So in both of these equations, we can conclude that the first reaction has a positive Q value, which indicates energy released due to the exothermic reaction, since the Q value is positive. The second reaction has a negative Q value, which indicates energy absorption due to the endothermic reaction. So this is about the comment on the result. So now let us move on to the threshold energy. The threshold energy is defined as the minimum kinetic energy of the incident particle, which will initiate an endoergic reaction. Threshold energy can be calculated by using the center of mass coordinate system. So we need to know about the center of mass coordinate system. Generally, in experimental nuclear physics, all observations take place in a reference frame that is at rest in the laboratory, and hence we use laboratory coordinate system for the case of experimental nuclear physics. Whereas in the case of theoretical point of view, the motion of the center of mass is of no consequences for the properties of nuclear reaction. So it is often more convenient to use a moving coordinate frame in which the center of mass of the two colliding nuclei is at rest. So the frame is moving in which the nuclei and projectile are at rest. So this system, what we consider, is called center of mass coordinate system. For the collision in center of mass coordinate system, the linear momentum is always zero before and after the reaction. Let EK1 be the kinetic energy of the incident particle in center of mass coordinate system. An endoergic reaction is possible only if EK1 is greater than or equal to the Q value. Let M suffix R be the reduced mass of incident particle and the target nucleus. Then the reduced mass, which is equal to the product of projectile mass and target mass divided by the sum of projectile mass and target mass. So here EK1, which is equal to half mv squared, that means here m is the reduced mass, so let us substitute the value. So from equations 1 and 2, we get half of the reduced mass into V1 squared greater than or equal to Q. And by modifying this, we get the kinetic energy, which is greater than or equal to this value, so that the threshold energy, which is equal to 1 plus m1 by m0 into modulus Q. So, or otherwise we can say the threshold energy, which is equal to m0 plus m1 divided by m0 into Q. This gives threshold energy expression. So this is the energy This is the minimum kinetic energy of the incident particle which could initiate an endoergic reaction. So threshold energy of an endoergic reaction. So let us calculate threshold energy of an endoergic reaction. In an endoergic reaction, minus Q is the energy needed to excite the reaction. That means the Q value is negative. This energy is supplied by kinetic energy of incoming particle. If minus Q energy is to be absorbed in the reaction, then the incident particle should supply some additional energy to minus Q, since part of kinetic energy is given to the compound nucleus. Here compound nucleus is the unstable nucleus formed by the collisions of a projectile with a target nucleus. So the minimum kinetic energy which the projectile should possess so that the nuclear reactions may take place is called the threshold energy, as we already discussed. Let Mi and Vi be the mass and initial velocity of the projectile. Let M suffix C and Vc be the mass and velocity of the compound nucleus. Applying conservation of momentum principle, we have MiVi, the momentum before collision, and MCVC, the momentum after collision. That means the compound nucleus, momentum of compound nucleus. So from which we can find out velocity of the compound nucleus, which is MiVi divided by MC. So kinetic energy of compound nucleus, that is half MCVC squared, which is equal to half MC, and instead of Vc, let us substitute this value, so we get this equation. So now the energy available for the reaction is the difference between the incident energy, that means incident projectile energy, and the emerging nucleus energy. So EK1 minus EK2. So the energy available for this reaction is the difference between the energy possessed by the projectile and the energy of the compound nucleus. That is the energy transferred to the compound nucleus from the projectile. The remaining energy is the actual energy available to start the nuclear reaction. So now we shall calculate the energy available for the reaction. So this is the difference between the kinetic energies. So let us calculate the differences in this way. So but here MC, that means the compound nucleus mass, which is equal to Mi plus Mt, where Mt is the mass of the target nucleus. So we can substitute so that we get the final equation. So here it is half MiVi squared into Mt by Mi plus Mt. It's because Mc minus Mi is Mt. And in the next step, since it's an endoergic reaction, the Q value is minus Q. So we have got the threshold energy expression. It is E threshold is minus Q into Mi plus Mt divided by Mt. So this is the expression for threshold energy of an endoergic reaction. So now we shall discuss one problem based on this threshold energy. The Q value of the Na23 within bracket n comma alpha F20 reaction is minus 5.4 million electron volt. Determine the threshold energy of the neutrons for this reaction. So the given Q value is given and the reaction is Na23 within bracket n comma alpha F20. That means the target nucleus is sodium and product nucleus is fluorine. Within bracket n comma alpha is given. That represents n is the projectile particle, alpha is the eminent particle. So now let us find out the solution. Here Q value is minus 5.4 million electron volt, and Mi, that means mass of the projectile, which is 1.00865 AMU, and the mass of the target, that is 22.98, that means mass of sodium. So now we know the threshold energy equation. This is minus Q into Mi plus Mt divided by Mt. Mass of the projectile, mass of target divided by mass of target. So by substituting these values, we can get the threshold energy value. This is 5.635 million electron volt. That represents the positive value of the threshold energy. So in this lecture we have discussed about Q value equation, threshold energy, and a few problems. Students, hope you would have understood the concepts. In the forthcoming lectures we are going to discuss about nuclear fission and fusion reactions. These are the reference books used for the preparation of this presentation. Modern Physics by R. Murugesan and Kritika Sivaprasad. Elements of Nuclear Physics by M.L. Pandya, R.P.S. Yadav. Nuclear Physics of Stars by Christian Liadis. Students, until the COVID situation changes, please stay at home, wear mask and sanitize your hands when you are going out. Stay safe. Thank you.